Testing, 1, 2, 3, 4. Sorry again, people watching remotely. This is why you should come to class. We're doing our best, but we're not the perfect AV people. Okay, so we can sort of get all these marginals, and I just did this in very explicitly, right? Like just working out all these equations. There's a general algorithm. This is the one from the book called variable elimination, where you're basically given for any graph, you're just given the graphical structure, the parents and the children. You're given the values of the variables you observe, and you're given some way to access the factors, and it comes out, it outputs one of these tables, essentially. So this code that I was doing in very explicitly, you can generalize it. We're not talking about it in this class, but I want you to know that it exists. Yes?
Is the table that this outputs like either a joint or a conditional or?
Yeah.
Yeah, is any of those?
Yes. So you can basically say for any variables in my model, if I observe that, if I'm given or I'm observing these variables, and I want to know these other variables, and I don't care about these third set of variables. So like the prior on bed in our example says, I don't care about the location. I just want to know this marginal that's only over the bed. The joint says, I want to know about A and B, and I'm given nothing. Like there's no observed values. A given B says, I want to know, I'm given a particular value for B, and I want to know the conditional distribution over A. And you just get, and if you're willing to variables, there's obviously a lot more combinations of that. And those questions correspond to real things in the world, as we'll see. But you actually, in practice, you rarely use these kinds of exact algorithms with CPTs. You usually assume assume the network takes a particular form that lets you do things more efficiently than this. But it does exist, and it's important to know that it exists, because I feel like this is sort of what's driving a Bayes net at the underlying level. At the end of the day, you can get anything from the joint, and there's an algorithm for it. Okay, so let's go back to localization. So this was our problem from last class. So we're going to change the problem now. So what we were thinking now is like, it's sort of timeless, right? Like here I am, I've been dropped into the world. I get to make one observation, and then I want my marginal. I want to know probability of location given whatever observations I made. Why isn't that what really happens? What's wrong with this? There's lots of things wrong with this model. What's one thing wrong with this model? Yeah.
All of your possible locations might not be so nicely discretized as 3 places.
Yes. Great. Yes. So my locations might not be discretized in 3 places. And you guys, in your particle filter, there's lots more than 3 locations, right? Like you're in this big grid, and I don't know how big the maps get, but like 100 by 100, 1,000 different grid cell locations. So that's still discretized, but it's pretty big. And that's one of the reasons why we need to do more tricks in the particle filter land. What else? Yeah.
We don't necessarily know if our observations are like objectively correct based on whatever model we're taking them from.
Yes, exactly. That's really good. So when I showed you this code here where I made up these numbers. I just pulled them out of the air. But who knows if they're right? Like maybe, and it might be the case that, like, let's say that I go to MIT and I count up in the MIT dorms these distributions. Maybe that's the same as Brown, but maybe not. And maybe even if I did it, let's say I counted them all up at Brown, and then I waited a year. Like these numbers, new students come in, and students move out, and furniture gets moved around, and buildings are repurposed. Maybe they're not good anymore. So keep making sure these numbers are the right numbers is really challenging, really important. A lot of what you have to do to make it actually work in practice is about getting these numbers right. And there's lots of tricks for that. What else? Is there more information that I would have in practice? If I was like a robot driving around somewhere, is there more information I could be using?
Like, if you just get plopped in a room, all you can see is what you can see. You can't, like, look around or move around.
Right, I can move.
There could be a bed behind you.
Yes, exactly. I can move around. and I can take more observations. And maybe if I can't take more observations, I would know more things, right? Like so even if we just stay in our 3-room world, I could look around in the other rooms and see what my camera says, or I could just, look behind me or run my camera detector again and just hope that this time it works better or gives me a different answer. So by collecting more information, I can increase the robot's knowledge or certainty about what it thinks is out there in the environment. So that's that's the particular type of way that we're going to fix the model today. However, in the project, so the person who said like the number of locations is really small, you're going to see how to fix that problem using approximate methods with the project. And there's sort of all of machine learning and all the graphical models to fix all of these other problems, and we don't even know how to fix them all. So especially that problem where the numbers come from, that's an ongoing open area of research in robotics right now. And a lot of people are struggling with where to get data from and thinking about the internet and Amazon Mechanical Turk and collecting large data sets of maps of different buildings, and we haven't really figured out the answer. The Google car is actually an interesting case study of this. So who's heard of the Google car? Yeah, so the way that they work, they call it creating digital infrastructure. So the Google car is able to drive autonomously only in places where they've previously driven with a person, and they collect all of the data, the laser scan data and the radar and the camera images, so that they know what the street is supposed to look like, and then they can diff what the street looked like when they were driving through with what it looks like right now, and the difference is the cars and the obstacles and stuff like that. And that's a major thing that they've done to make the Google car practical and safe. It's still not like commercialized, but like that's how they've driven hundreds of thousands of miles, by collecting data to fill in those conditional probability tables, different models and all that. But like that's what they're doing, and so there's a lot of effort putting into these other areas too. Okay, so to formalize this problem, what we're going to do is we're going to use different variables. This is sort of the standard variables that people use when they talk about Bayes filters and localization and particle filters. So x of t is my state at time t. And that's going to be the same as it was before, our 3 different locations. So it's going to be kitchen, bedroom, and living room. Z of t is my measurement at time t. So what do you think our measurement would be if we're going to kind of adapt this model?
The object you see in a room?
Yeah, whether or not I've observed a bed, or the set of objects that I've observed. In this case, just to keep it simple, we're just going to have a bed detector. But yeah, whatever observation that I've made. And then the control, so this is the new thing, the control input. So what would that be? Yep.
Switching rooms.
Yeah, so I get to decide what I want that to be. But what it's supposed to be is like how I decide. I'm a robot, I'm an agent, and I can change my own state. And this is the control input that I send to my motors that causes the state to change. So if I know for sure what my motors are going to do, I could just directly model it as switching rooms. So like my control input is I'm now going to teleport to the kitchen, or I'm now going to teleport to the living room. And afterwards, I know for sure that I'm in the kitchen or in the living room. But what lots of times is true is that I don't know for sure. So like let's say that my motors slip, or my software could crash, or somebody could close a door in front of my face, and so I could try to drive through a doorway and it didn't work. So a lot of times what people will say is, look, I'll try to drive to the kitchen, and with some probability, 90% probability, I'll succeed, and I'll be in the kitchen afterwards. And with 10% probability, I'll fail. I'll stay where I am. That's a common model, but you get to pick what you're going to do. And then the goal of the robot over time is, you could have lots of goals here, frankly, but our goal today is to localize ourselves. Tell me what my state is at any particular time. Now, I could also start to think, and when we get to decision making under uncertainty, we'll start to think about how you can actually control your control input in order to use that to increase your certainty about the state. But here we're just going to play with really simple control policies, and then just given whatever control we decided to do, let's say somebody's driving the robot around, or something. We don't get to pick it, but we do get to know what it is. We're going to try to estimate our location over time. So we don't just get one, we get a sequence. And at every time step, we sort of update our belief. Okay, so in math, what that says is what we want to know is P of x sub t, my state at time t, given the observations. So for all the past time steps, I've observed whether or not there's a bed, and my past control inputs. So I know I try to go to the kitchen, or try to go to the living room, or I try to go left or try to go right. Yes?
Does your control input come before or after, like, your current state? Like,
Yeah.
do we only go up to t-1, or is it like?
So we'll talk about that. People usually, when we get to the algorithm, usually you do the control input first, and then after that, you take an observation. So after you do the control, you can update your belief over where you think you are. And then after that, you can take an observation and update your belief again, and then you do a loop. So because it's a loop, you could decide to start the loop somewhere else.
You do something before you do your first state measurement.
You do something before you do your first state
Like
measurement.
You have a control input before you.
You don't have to. So usually you have to input to this algorithm a belief at time 0. And there's two in practice. Again, you could pick that to be whatever you want. And in a Jaynesian sense, you should pick it to be what your true belief is over your state. Usually in practice what that means is you either know for sure where you're starting, so you just say I'm starting in the kitchen, or you have no clue, and so then a uniform distribution over all of your locations. Those are the two most common situations. Yes?
So when we say P of x of t given
Yep.
those two variables, we're saying like for each of the given states we would have to calculate that, like that xt refers to like one specific state.
Yes. Yes. So at each time step, so the way that we're going to sort of model this, and we could decide to take more than one observation before we take a control input. We could interleave it in lots of different ways. But the way that we're going to model it today is we're going to say at each time step, we're going to send a control input to the robot. It could be nothing. So in the code I wrote, you can go left, you can go right, or you can stay where you are. And then we're going to take a picture, and we're going to run our bed detector on the picture, and we're going to see if it detected a bed. And then we're going to take another action, and that's x sub t. And then we're going to take another action and take another observation, and that's x sub t plus 1. And we're just going to keep doing that. Yes?
So under this model, does like where you thought you were in prior time slices not necessarily inform where you think you are now?
That is a great question. So what's kind of scary about this? Like there's like a lot of these z sub t's and u sub t's. So as our history gets longer, this thing, and they're on the given side too, right? So this thing is going to get more and more and more complicated. This distribution. So what you're talking about, does our prior estimate inform our current estimate? In general, no. So we haven't made assumptions about that yet. But what we're going to do is make assumptions, the Markov assumption, that which we'll talk about next, which will let us use our prior estimate to update our belief over our current estimate, so we don't have to worry about the previous history of all the observations. Okay? So that's what the conditional independence assumptions are going to buy us. If we didn't make them, we would have to worry about every single possible sequence of states that we were in and marginalize over them all with the whole sequence of observations, and it would get really intractable. Yes?
So just to clarify, as you go through the time steps, you would update U to account for your previous information?
Update U, so you get to know U for sure. U is I either saw a bed or I didn't see a bed.
Okay. So you would update your belief as to what room you're in?
Yes, exactly. So x of t is, in this toy problem, is what room I'm in. And I don't get to know that for sure. That's what I want to know.
Okay.
Does that make sense?
Yeah.
Okay. I could decide, in these different, it's actually one exercise I want to do at the end of class, hopefully we'll have time, is to come up with other things that we could have for the state, the measurement, and the control input. But I think it's going to be easier if we just take the sort of discrete small world case first and see how it plays out, and then do that exercise.
I thought Z was whether there's a bed or not, and U was if you knew for sure whether you would know.
U is your control input. I think I misspoke before. Z is my observation, so there's a bed or there's not a bed. U is whether I decided to go left, right, or stay where I am. And in my world, I made it a. So with my U's, I had to make a decision about like the structure of my world. So let me look up the order so I get it right. So I gave my world a little structure. Kitchen, bedroom, and living room. So this is the kitchen. This is the bedroom. I guess it's a really non-standard layout for a house, but this is what I had. It's like a, what do they call them, railroad apartments? And this is the living room. This is actually the structure of my sister's apartment in Brooklyn, although I didn't plan that. All right, so if the robot is here, you could be, I'm gonna go left, and if I try to go left and I'm already at the end, I stay where I am. And if I try to go right, I go to the right. And if I do nothing, I just stay where I am for sure. And then I add a noise term. So if I try to go right with 90% chance, I go right, and with 10% chance, I stay where I am. Yes?
Do you know if you try to go left and you can't? That would be a really good, easy way of knowing.
Yeah, you don't get to know.
Okay.
So you can decide. Actually, you could decide that U is zeros and ones, and then we're back to logical world. And so then if I know that it always, like depending on my noise terms, like I can just reach certainty about where I am, even though I have no observations, because I could just go left, 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 left until I've done it 3 times, and if it always works, eventually I'll know I'm in the kitchen. And then after that, if there's no uncertainty about my movements, wherever I go, I know where I am, because I can just self-model myself, right? Does that make sense, everybody? But really, in practice, U is noisy. So I'll try to go left and I won't succeed. And then I want to correct it, and that's what the observation will let me do. So I can get estimates of where I am from the observation alone, from the movement alone, and I can do even better by combining them both together. So that's what we'll sort of talk about. Okay. So we're going to make 2 independence assumptions, which I'm going to give in math first, and then we'll look at the graphical model of them. So the first one is this Markov assumption. So when you're talking about estimating previous states from next states. So if I know for sure, what this is saying is if I know for sure all of my previous states, all of my observations, and all of my control inputs, and I want to estimate my next state, then I'm going to assume that only depends on my previous state and my control input. So it might still be uncertain, but it doesn't depend on the whole previous history of my observations. It just depends on my control inputs. It just depends on my last control input. So is this always true? Can we think of an example where this is false? So where my next state depends on, let's say, previous control inputs besides the most recent one. Yes?
Like if you're in a river,
Uh-huh.
you're in a boat, and you do nothing, you might end up one way or another within your control of that.
That's actually, I think, still captured in this, because this can be a distribution. So I could do nothing, but my previous state would include, let's say, the current in the river. And then that would tell me I could, with some likelihood, go backwards. Yeah?
Like the action failed.
If the action failed.
If you're in the room and you're trying to go left, but you can't go left. But all you know is that you tried.
If you can't go left, but all you know is that you tried. Yeah, so if your action has some kind of memory, so let's say that like I have a finite amount of gasoline in my boat in the river, and I've run my gasoline all the way down to almost empty, and then I give it a shot of gas, and I run out. This distribution might change depending on my past control inputs, my past actions about which sort of affected the gasoline. So this is one of those independence assumptions that's not true in general, but it sort of makes our lives a lot easier if we make it. And it's true in a lot of cases. Yes?
So why do you not factor in the measurement of time t under this assumption?
Why do we? Yeah. Well, so our next independence assumption will be about the measurement. So the reason we don't is that what we want to do, in general, when you're coming up with these models, I think what's also maybe a little misleading is like I'm showing you what people usually do because it gives you this nice decoupling. So if I didn't do that, if I tried to incorporate the measurement and the control input at the same time, I wouldn't get the decoupling that that sort of works out to be a really nice thing. Because usually in practice, like if you think about your robot, like people when they build a robot, like they'll look at different sensors, and like you can buy like all these different cameras, and there's the Kinect, and there's lidars, and there's radars, and you sort of look at all the different trade-offs of your sensors, and then there's like separately actuators. So like if you're doing a car, even if you're doing a car, like you say you're going to do a vehicle that goes on the road, there's all the different cars you could pick. I used to work on a robotic forklift. People worked on motorcycles. There's lots of different actuators. So what this way of breaking it down does is it sort of reflects that decoupling that exists in the world. Does that make sense? Okay, let's keep going and maybe it'll be clear. So people call this the state transition probability. So this just says, how does the robot's actions affect the world, independent of all of the observations? So the next independence assumption we're going to make is related to the observation. So this is sort of what we know about observation. So this is the observation at time t, given knowledge of my previous states and the previous observations and my previous control inputs. And what I'm going to say is that my observation right now only depends on my state right now. So it doesn't matter how I got to where I am. It only matters that I'm there. Okay? And again, this might not be true. Like let's say that I'm using a camera and it's raining outside, and if I went outside, my camera lens is going to get wet, and then I come back inside, and my observation might depend on the fact that I was outside before, and now my camera is wet. Okay? And so I would need to know the previous states that I was in order to get a more accurate version of this distribution. We're saying that we're just going to ignore those types of cases. The observation only depends on my current state. Does that make sense to everybody? And it corresponds to this model here, where this is my state, and there's an arrow from that to the observation that I get to observe. And this is called the measurement probability. It gets some measurement, observation, or measurement of what's going on out in the world. So for your projects, what are the states and what are the measurements? Yes?
The states are just like the random
Yeah.
positions.
Yes.
Measurements are just like the wall for.
Right. Exactly, your laser scans. So in this problem, what are our, we said it before, but why don't somebody tell me again, what are our states and what are our measurements in this problem? Yeah.
Room and photo? Like
Yeah.
What room you're in and what photos?
Yeah, particularly whether my bed detector fried or not. Yeah, so I could decide to have it be the photo itself, and then people do like there's a lot of different choices I could make about my states and my measurements would give me different trade-offs. So the next thing we're going to do is talk about the graphical model for this. So what I'm going to do is kind of put the variables up. Maybe I'll do it on the whiteboard. That might be easier. And let's see what this looks like graphically. Okay, so we have u of t, u of t minus 1, I'll make sure the indexes are right, and x of t minus 1, x of t minus 1, and z of t minus 1. So what else do I need to capture these two independence assumptions? So first of all, I can draw an arrow on this right now, just with what I know. The second thing we're going to do is add some more nodes to this graph. So what arrow can I draw right now? Yes?
From xt minus 1 to zt.
That's right. xt minus 1 to zt minus 1. So I'm saying that my observation at t minus 1 only depends on my state, nothing else. So now I'm going to draw some more nodes. So it's just going to be ut and xt and zt, and I'll do t plus 1 too. Plus 1, x of t plus 1, and z of t plus 1. So now what other arrows can I draw? Yeah.
Well, you can draw an arrow from x of t to z of t.
Yep.
X of t plus 1.
Yeah, so I can draw the same arrow. So at every time step, no matter what t is, it's always true. It only depends on my current state. What else?
X of t depends on x of t minus 1, and probably x plus, or x of t plus 1 also depends on x of.
Yes, my next state depends on my current state. So it's sort of like I'm moving around, and I can't go, like, the way to think about it is, like, I can't go too far from where I am right now. Based on where I am right now, that tells me something about where I could possibly be in the future. What else tells me about how my state's going to evolve in the back?
The next state depends on the current input.
Yeah, we're actually going to say it depends on the previous control input. So I could have decided to do it in another way, but it would just have to update all my indexes in the math. So I'm going to do the way that my slides work so that we don't get confused. But that's exactly. So the way that my state evolves depends on my control input. And this guy, I drew it to make it complete, but like he depends on something on the next state that's not in the picture. Does that make sense to everybody? Graphically? Okay. Cool. And this is pretty typical. So in a lot of our graphical models will be like this, where there's like an infinite set of nodes, and there's some kind of repeating structure that happens. This is how HMMs work. This is how conditional random fields work. This is how Bayes filters work. It's one particular class of graphical models, one particular way of factorizing the world that turns out to have lots of different applications. And we're talking about one, which is the Bayes filter. OK. So here's the slide version of all this. So that's just what I drew. OK. So now I'm going to do one more bit of notation. So what we want to know is probability of x of t given our observations and our u's of t, and this corresponds to our belief. Okay. I find these algorithms to be, it's kind of confusing, like when they switch between probability notation and this kind of functional notation. But it can kind of, when you actually code it up, I think it's easier to use belief of stuff, because it turns out to be a nice name for a variable. So that's why people do that renaming. OK. So now I'm going to give you the algorithm for a Bayes filter. So this is what we're going to do. At each time step, we're going to alternate between predicting where we're going to go based on our control input. So this is the distribution over my current state given my previous control input and my belief over the previous state. So where do I think I am based on what I did? And then using that, we're going to update, we're going to incorporate our measurement probability. So without worrying about exactly how this is, we'll go through the derivation of how, and then we'll go through the code. The high-level pattern of this is at each time step, we update some data structure that's modeling where we think we are with our eyes closed, just knowing what control input we sent. And then we open our eyes, we take an observation, and when we update that based on the observation, and then we loop and go do it again. So we take a new control input and then a new observation input. OK. So to do this, and these are called like the prediction step. This is called prediction because I'm predicting where I think I'm going to be based on the action that I took. And then this is the measurement step where I forget what they call it. But the observation step where I observe the world, I get some observation, and that tells me something about where I am based on what I can see. Yes?
This is the thing that looks like an N.
What is the thing that looks like an N? Yeah, this is an eta. That's the name of the Greek variable. And what it is, we'll derive it. So I will show you. But what it is a normalization constant. So it's something that does not depend on x of t. And it's it's sort of the magic number that it has to be to make this product a probability distribution. And it arises from Bayes rule. And we'll see exactly how when we derive it here. So So what I wanted to do was sort of show you where these two steps come from. And what they're trying to do, what we're trying to do is write our belief of the measurement update and then of the prediction and then the measurement update in terms of stuff that we have, right? According to this factorization, in terms of stuff that we can do with our CPTs. So the problem with this form of the graphical model, what makes it tricky is that because it goes on forever, we can't use our exact inference algorithms. We can't just use a CPT to do this because our CPT would have to keep growing and growing and growing. So what we're doing here, the sort of trick that we're playing, is we're factoring it into these two components. And we're alternating computing these two different conditional likelihoods. And we write each conditional likelihood in terms of the other conditional likelihood. All right, so this conditional likelihood, the prediction step, is written in terms of our last observation step. And our observation step here is written in terms of our last prediction step. So we alternate back and forth between these two steps. So the next thing we're going to do is sort of the math of this. So like, why is this the right thing to do? So here is what the prediction step looks like. I want to know my current position given my previous observations and my previous control inputs. Right? This was like the hard thing that we weren't quite sure how to do. So and we're going to write this in terms of the observation probability. So we're going to sort of use the first thing we're going to do is sort of use integrals instead of sums, but we're going to use the rule of total probability to give you this integration over x of t and x of t minus 1. So that's the sum rule. And then we're going to factor this. So this is still exact. This is the product rule, right? So I'm going to take my x of t. So this is just adding x of t and sticking the integral around it, around that new joint. Then I'm going to take x of t given x of t minus 1 and x of t minus 1 given all of my previous steps. So what am I going to do next from here? So let's look at this. Yes? So can I write this first term in a simpler way? So this is saying my next state given my previous observation, and my previous control input. So here's my model here. My next state. Yes?
Could you just,
You first. I'm sorry.
The state
Yeah.
transition thing that we did, so it just depends on.
Exactly. Yes. Exactly right. So
Does that not use sub 1 if you use sub d?
oh. Yeah, it should be 1 to t. There should be a colon in there. Sorry about that. Yes. U sub 1 to t, all of the u's. Sorry, guys. I can fix it. Yeah, I just put an underscore instead of a colon. I don't see it. Oh, the first one. Yeah, sorry about that. All right. Yes. So I can write this in terms of something simpler. And I can also do the same thing. So this is just some kind of like indexing bookkeeping. So my previous state doesn't depend on my current control input. The state that I'm in only depends on the previous control inputs and the previous observations. Make sense? Okay. So this is making our conditional independence assumptions that our model was telling us we were allowed to make. So then we do this sort of notational stuff where this bell bar corresponds to the prediction step without the observation, and the without the current observation, right? So it's taking into account the previous observations, but not the current observation, but is taking into account our control input. And then this is using that BAL notation. So this is just replacing this with this. Okay, so that's our first step. And all we did, the reason, like, so we could have made different decisions about the expansions that we did to rewrite this distribution in terms of other stuff. The advantage of doing it in this particular way was we got this nice recursive form where we can write BAL and BAL bar in terms of each other. So this is writing BAL bar in terms of BAL. Okay, so now we're going to do the other direction, the measurement update. So here's sort of so this is like what you start with, basically, the x sub t given z of 1 to t and u of 1 to t. And a clue when you see these normalization constants in there, there's probably some kind of Bayes rule thing going on. So the first thing that we do is apply Bayes rule to move the observation to the other side. So this is just the product rule twice. So it's P of A given B equals P of B given A times P of A over P of B. All right? If you haven't derived that, I recommend that you derive it. So it's just this thing on top. If you ever get confused, this is the joint. This is the joint probability, and then we're dividing by this to get a conditional probability. It's writing them in terms of each other. So here, what is our A and what is our B? Yeah.
A is x sub t and B is
Yes.
givens.
And B is?
Z sub 1 to t and B sub.
So that's a little tricky. So is B really, is all of that stuff, or is it something less?
It's just Z sub t.
It's just C sub t. So this is a very common pattern that happens when you apply Bayes rule. So if I just wrote it with A and B, but really what it is P of A given B and C equals P of B given A, C, P of A given C over P of B given C. So, right, so C is just there, and it's always on the right side in every single equation. Yes?
Never mind.
Okay, so here, everything, all the stuff that's here, we're privileging our current observation. We're switching that one to the other side, but everything else, z to t minus 1 and u's are all on this side. And that's the only thing that we did here. We applied Bayes rule on z of t and x of t. Yes?
Is there commas or is it bars for the for the P of B given C, P of A given C?
P of B.
Is that a joint distribution or is that a conditional?
Given A and C. This is a conditional distribution on A and C. So if I was using the Jaynes notation, it would be A, C, A times C, A and C.
But the other two ones.
P of A given C?
Yeah, because up there you have commas, right?
Up.
It's okay.
That's the notation we've been using.
Yeah, it's
Yeah.
notation confused, I guess.
Okay.
Yeah, that's not z given x and z. It's
Yeah, the condition rules over everything. Everything is either on the left side or the right side. There's no third
Yeah.
place. Yeah.
Oh, no.
So maybe if you've seen like parameter vectors, sometimes people will write a semicolon and theta. Have you seen that notation? P of A given B theta. Have you seen that? That's not confusing you? Okay. I hate this notation too, but people use that, and it also kind of interacts with the bar. So we will talk about it since most of you haven't seen it. But yeah, so the bar rules over everything, and commas and ands are kind of interchangeable. Okay. So now what can we do? Can we make some independence assumptions about this?
Z only depends on x.
Yes, right. So z sub t only depends on x sub t. So what does that say about this term up here? You don't need any of the other stuff. Yes. Bayes rule. So we can get rid of that. And then I think that's it. So if we make this conditional independence rule. So the next thing we do is this eta thing, right? So this thing, somebody asked me what eta was. We're writing this as this constant here. And this is another very common thing, like this normalization term. special about this normalization term compared to the other two terms up here?
Doesn't have to do with the state at all?
Yes, it doesn't have to do with the state at all. So I could try to write it in terms of the state and sum over, like write it as a joint and sum over all possible states. But it turns out that as long as, like, its only job is to make this thing back into a probability distribution. So as long as I make sure that whatever product I get up here for all these different terms sums to 1, I don't actually need to compute this using for my givens, like, if that makes sense. So in practice, what we're going to do is this distribution is going to be a vector where we can look up for each value of x of t what's the probability. And when we take this product without eta, it's not going to sum to 1. It's going to be larger than 1. Then we're going to divide by the sum, and magically we'll just make it sum to 1, right? You can sum and then divide by the sum, and suddenly it's normalized.
So
Yes.
basically the term on the bottom is just how much we're going to say that we trust the current observation based on the past ones, like sort of how much we take that into account. We just like make it a constant.
It's how much the current observation, given the past ones, marginalizing over all of the possible values of my states. So I could write this in terms of the joint on x of t and sum out x of t. And if you want to think about like what it really is, that's what it really is. Like, it's this weighted average on x of t of getting this observation. However, I don't actually computationally need to do that because it's going to work out to be the thing that makes this whole thing normalized to 1. So I can compute it in an easier way in practice, which is why people always write it like they just write this n thing, because even though you could write it in a joint, and if you computed it that way, it would work. In practice, you don't need to. So we can just in the code, it'll be simpler. All right, and then we do this step of replacing everything with Bell and Bell bar. Okay. So now we've written our belief in terms of our prediction probability. So if we go back to the algorithm, there's something else that annoyed me about the algorithm. This is actually d sub x sub t minus 1 that they're integrating over. And it's really confusing that they wrote d sub dx. Like, you don't know what x actually is. Anyway, we can go back to our algorithm, and we get our belief over x sub t as this integral, which we derived here. Oh, sorry, we derived here, right? So this was the product rule, the sum of the product rule and a conditional independence assumption to get this. I wrote the t minus 1 here to make us happy. And then the second step, which is the measurement update, which we derived here. And then that lets us do this nice little algorithm. So the next thing I want to do is implement it and show you what it looks like in practice. Okay. All right. And actually, well, I guess base filter is good enough. So to start, what I did was make this. I made this little world where it's. Oh, I erased it. That sucks. Where we could be, let's see, kitchen, bedroom, and living room. I'm going to draw the map so we don't get confused. Kitchen, bedroom, living room. And we're in each of these rooms, when we take an observation, we have some probability that our bed detector will fire. And that is from this table I showed you before. So if you're in the kitchen, most likely you won't see a bed. If you're in the living room, most likely you won't see a bed. If you're in the bedroom, most likely you will see a bed, but it's noisy. And the question is, how can we integrate these observations over time to come up with more information? Okay, so here's sort of this is sort of like an empty version of the file. So what we're going to do is initialize our world state where we're in the bedroom. And our world state, like this guy is basically like a simulator of the real world. So even though in our code we could actually look up and see where the robot really is, in real life the robot doesn't have that access to that oracle. So don't get confused by that. Like, we're going to be estimating the true value of the state, like pretending that we don't know what it really is. So our belief, this is our bell of x of t from the Bayes filter algorithm, is going to be initialized to be uniform over the possible rooms. So how are we representing the belief over the states? What does it look like in Python? It's right here. Yes.
It looks like it's a uniform distribution.
Yes. And so what? So it's a list, right? So what is each element of the list telling me? So what's the value? First of all, what type of value is in there? I mean, it's a uniform distribution, right? So it's a probability. What did you say?
All values in this set is equal. Right?
Yeah, they're all equal. So this guy is I guess what I wanted to say is, like, what's the data structure of it? It's a list, and how many elements are there in the list?
Length of the location domain.
Yes, so the number of rooms that I have in the world. So this is a very common way of representing distribution. So before I made like this class, a lot of times people will use lists or arrays. And what this is saying is this is supposed to be that conditional distribution. It's got a sum to 1. So for each element of the list, it's the probability that the robot is in that particular location. And I'm initializing it to be uniform. And this is just printing it out and then pausing. And then for each time step, this is like not doing any belief updates or anything like that. This is just showing the frame for the filter. At each time step, I am printing out the real location. I'm picking a UT. I'm going to do it randomly. And then I'm updating my state based on that control action. So I'm sending that to the world and having something happen. And what I basically did this morning is, if I go find that code, def move, is with some probability we do nothing. So with some probability we just assume that the action failed. Maybe somebody closed the door in the robot's face and it couldn't transition. But otherwise, if it was left, so if we're in the bedroom, we're going to go left. If we're in the kitchen, we're going to stay where we are. If we're in the living room, we're going to go to the bedroom. And if it was right, it's the reverse. So I just wrote this little transition model in our world simulator. So it's just a bunch of code that does that. And then I'm going to take a picture. So this is saying state.observation, and it's going to tell me bed or no bed in this particular world. So if we go to what that code looks like, observation. So here I implemented this in our simulator by sampling a value from the CPT, from the true CPT. Of course, in real life, I would have to characterize what my actual bed detector was doing to get this number instead of making it up. But here I just simulated it. And then we're just printing out our belief over time. So let's try to run it. So here it's let me make it bigger. So here we're printing out the initial belief values, right? And as we said, it was uniform. So for each of these guys, kitchen, bedroom, and living room, it's uniform. So now I'm gonna hit my real location, which again, remember, we don't know. The robot doesn't really know it, but we know it because we're simulating it, is the bedroom. I picked an action, which was to do nothing. And my new location after the action is I'm still in the bedroom. Then I get an observation. So I'm drawing that from that distribution of 0.9 and 0.1. And in this particular case, it happened to say there was a bed. And then I'm ignoring the observation bit because, again, I'm doing nothing in the filter right now. So my belief is unchanged. I still have no idea because I haven't done any updates. OK? So now let's do it again. So I did nothing again. Not a very interesting robot. And I observed a bed. Not very interesting robot. I wonder if I have it set to always do nothing. I had that for a while, and I was testing this. Nope, it's just getting unlucky. So let's see. Oh, there we go. It moved left. All right. So it moved left, and now it's in the kitchen. Bedroom, kitchen. And then observation is no bed. So now I'm moving nothing. I want to see one where it tells you the wrong thing. I moved left. I'm still in the kitchen. No bed. No bed. Okay, here's one where my detector failed, right? So I'm in the kitchen, but my observation was a bed because I have a noisy detector. So this is just showing like what the world is doing to the robot, and we're sort of ignoring all the information. So the first thing I want to do is write down the bell bar for our little robot. So what does bell bar look like as a data structure? So we're going to do our prediction step. What should it be? So we're not going to fill in like all the values. We'll do that. We'll have to do some code, like more code to do this. It's going to be like 4 or 5 lines of code. But what's the type of it, right? It's a distribution over what? I heard some people say it. So let's look at our slides. So what's it? What is bell bar? A distribution over states. Yeah. So how many states are there? 3 states. Yeah. So it looks just like bell in terms of its data structure. So if I initialized, I'll just make an array. I'll make an array of zeros. That's pretty safe, right? Length of bell of x sub t. Okay. So that's probably wrong because it doesn't sum to 1, right? So there should be some numbers in there to make it an actual distribution. So how do we fill in those numbers? So what's that integral going to sum over? So for our little integral right here. Yep. Yes. So I want to iterate. So to do this integral, it's really a summation in this world, right? Because it's a discrete world. I'm going to sum over all the different values that x sub t minus 1 could have taken. How many are those? 3. Yeah. So how should I do that in code? What should that be? Yeah, for each loop, exactly. So for x sub t, I'm going to use this like notation of the index and xt m1 in enumerate location dot domain. So I'm just going to enumerate all the possible different locations. So let's print that out. Print xt m1. See what that does. So what's that going to do? Going to print out something, right? What's it going to print? Well, x sub t m1, I guess I didn't really tell you what that is. So x sub t m1 is like the actual state value. So it's just going to print out all the state values, I think. Yes. Kitchen, bedroom, and living room. All right. So now what are we going to do to make our integral? So we have to, it's like a summation, right? So we have to add stuff up. So actually we need an outer loop. Right, so this is the inner loop for the integral, right? What's the outer loop? Yes?
Oh, sorry, can you just talk about that Python syntax for a second?
This?
Yeah.
Yes. So all this is doing, so location.domain is a list of kitchen, bedroom, and living room. And enumerate is giving me a number, the index and the value. So this is going to be 0 kitchen, and then it's going to be 1 living room, and then it's going to be 1 bedroom, and then 2 living room.
So it's a list of tuples?
Exactly. Yeah, I can print that out if that's not clear. Let's try. Okay, so 0, 1, and 2. And that just lets me transfer. I could have used maps or something else, but that lets me transfer to different ones. So the next thing I'm going to do is do this outer loop. So the integral is in the inner loop over x of t minus 1. I need an outer loop over x of t, right? Because this guy is an array, and there's a value for each value that I can have x of t be. So for xt, idx, xt, in enumerate location dot domain. And then I'm going to make the summation, right? So something is going to say prob plus equals something. And then at the end, what do? We'll fill that in a second, but what do I do with that probability? What's that? Yeah, stick it in bell, bar, xt, idx equals prob. That make sense? So I'm just going to, for every value of x of t, I'm going to update my probability. So now what goes in there? So what's this?
Prior.
Yeah, so in terms of my code though, right, I have somewhere, I have a bel of x of t, right? So I can just look that up. xt, or is it t minus 1? So I can look up my last one, and I'm going to multiply it by, what's this? Not the integral, but this term in here. What do we call that probability?
Measurement probability?
The state transition probability. Yeah, the next one is the measurement probability. Right, so I have to know something about how my control input affects the world. And I coded this up before class, so I give us this function of this guy. And if you can see what it looks like. So it takes the index, or basically the state, the UT that I got, the XT, 1 IDX, and the list of all the locations. IDX. And all this is doing is this noisy transition model I talked about before. So like if we're at the wall, we stay where we are for sure. If we try to move left or right, we succeed with probability 0.9, and we fail with probability 0.1. And if we fail, we just stay where we are. That's the model. And we could use lots of different models in here, but that's the one we picked. Okay, now let's see why it doesn't like me. And define. Oh yeah, location.domain. Domain. All right. So now let's see what that does. So what we can do is just say that bel xt equals bel bar xt. And just see, as we move around our state space, how our belief evolves. And actually I'm going to make it even simpler. So we're just going to always move to the right. So what do you think is going to happen as we always move to the right? What should happen to our belief?
Living room.
Right, eventually we should get to the living room. So let's watch and see if that actually does happen. So here, initially we're uniform. I'm going to not print out all that extra stuff, if you guys don't mind. All right, so we move to the right. Our real state is, in fact, the living room. We succeeded at that. And now here's our update after we do that. So initially we had no idea, but now it's starting to put more probability mass on the living room because of this prediction step. And we're just now ignoring the observation. We'll get one and we'll ignore it. So we'll just keep going. Do it again, and it puts even more mass on the living room. It does it pretty fast because at the beginning it could have been in kitchen or bedroom, but now even if it was in the kitchen, it's probably in the living room because both those moves succeeded. Why isn't this ones here? And yeah.
Because the movements are noisy, so we don't know if we actually.
Yeah, exactly. So the movements are noisy, they could have failed. So I could have failed twice. I could actually still be in the kitchen. Not too likely, but it's possible. And we're able to model that. So if I just keep going, it's going to stick more and more probability mass on living room and less in the kitchen. Yes?
So right now we're only updating based on our controls, right? We don't
Correct.
take into account the observation.
Correct. So the next thing we're going to do is the observation. So let me show you what happens if we, before 5 minutes, if we do it random. So the world is a little less sure depending on how it goes. But this is a pretty good control model. So like as I move around the world, I can kind of know where I am. But using the observation, I can get even more certainty about it. So now let's do the observation update. So if we look at our belief over x sub t, what's that going to look like?
Eta. So we don't-
Well, what's the outer thing? It's going to be like before, right? A for loop over all that stuff. And then we're going to get some probability from something. We don't know where. And then we're going to say bel xt idx equals this probability. Okay. So the way we're going to handle our eta is by doing this. Bel xt equals bel xt over sum of bel xt. Okay? So this is just the trick to make it normalize. Make it sum to 1. All right. So now how do we compute this? So what's the kind of easy part? Bel bar, right? So what is that? Yeah. XT. ADX. Good job. And then what's the first term? So what do we call this term? The measurement probability, the observation probability, either one. So we got that. So we get this. You kind of have to know this too. Like I basically passed it in. I passed in all this stuff, which we don't need nearly all of it. But the location given the bed, and actually I did the kind of. I'm not the proudest of the way this code worked out. So I'm going to just, since we're running out of time, copy the update from before for my practice run. So bed given lock. This basically update to look it up in the conditional probability table in whatever form you happen to have. So if this was continuous, this might be looking it up in a Gaussian or something like that. Let's see. Oh, this is supposed to be ZT. All right. Let's see. So actually what I'm going to do now is tell the robot to do nothing every single time. So we can see the observation probability running on its own. See how it works. So here, I'm in the bedroom. I'm not moving anywhere. So I don't. So when I don't move anywhere, the control was not going to tell me anything, right? I'm wherever I was, and I'm still wherever I was, and I don't know where I was. So I'm just clueless. So now I observe a bed, and I do my observation update, and I went from not thinking I have no idea where I am to thinking maybe I'm in the bedroom. There's still some mass on living room and kitchen. Why? Because why?
There's noise on your
Yeah, there's noise on my detector. So I could have gotten a false firing of it. So let's do it again. Nothing, and then I observe a bed. So if I go, so as I observe more and more beds, I'm going to get more and more mass on bedroom. Eventually, I hope it will give me a false firing. I guess it's not. No bed. And you can see this one no bed put a little bit more, even though we're really small already, like it put a little bit more mass on kitchen and living room. So it's taking into account the stuff that we're able to tell our system about how the model works. And the more accurate our model, the more accurate our sensor model is, and the more accurate our control model is, the more accurate this estimate is going to be. And the reason that we do it this way is because it's pretty easy for, it's at least possible for us to directly estimate our sensor model and to define how we're going to control our robot, because like we built the robot, right? So we can just sort of say what our model is of how we control it. And then we can do these updates where at every time we're maintaining this distribution of where we are. So this is what you guys are going to sort of do for particle filters, but with continuous distributions and laser rangefinders instead of cameras. But it's still a Bayes filter. The math is the same. The code is different because we're making more approximations when we have really big state spaces, and we assume parametric forms for our random variables, and we sort of get the math to play out in different ways. Okay, so just to sort of finish up with a measurement update, Bayes filter. I want to emphasize again, I'm showing you one very common graphical model used for estimation and control in robots. It's just one. There's lots and lots of them out there. This one is really important. It's used in a lot of things, and there's lots of different tricks to implement them. So this one in class today, we used conditional probability tables. So we just had this CPT, conditional probability tables of all the different possible observations we could get, and we filled it in. You guys are going to see particle filters. If you've also seen something called a Kalman filter, it turns out if things are Gaussian, then you can work out that integral in a closed form, and you can actually integrate it in general and get a new form for it to do your update. That's called a Kalman filter. And then there's lots of other models in the world. These are just two. We won't talk about HMMs, but we will talk about naive Bayes classifiers in the next section. And you could go out into the world and find lots and lots of different models. And we'll actually have you come up with models in the discussion forum next week. All right, thanks guys. See you Friday. See you Thursday.